something changed. Less than a week after passing Earth, 3i Atlas, the interstellar visitor we've been tracking for months, altered its course. Again, trajectory adjustments have been observed since it entered the inner solar system, and here's what makes this moment different. Even with all our technology, all our observations, this comet keeps doing things we didn't predict. It's behaving in ways that challenge our understanding of how these objects should move through space. This isn't a drill, this isn't speculation, this is happening right now, and you're watching it unfold in real time. Stay with me for the next several minutes. We're going to uncover exactly why this interstellar comet won't follow our predictions, what the trajectory adjustments observed throughout its passage actually means, and why scientists around the world are paying closer attention than ever before. This isn't just another space story. This is about an object from beyond our solar system that's challenging our models as it passes through our cosmic neighborhood. Now, before we go any further, I need you to understand something crucial. 3i Atlas isn't from here. It didn't form around our sun. It came from somewhere else entirely, somewhere in the vast darkness between stars, carrying with it secrets about conditions we've never directly observed. It's the third confirmed interstellar object we've ever detected, and unlike the others, we're watching it in unprecedented detail. Every observation, every measurement, every tiny deviation from expected behavior teaches us something new about what exists in the space between solar systems. The December 19th flyby was supposed to be our best opportunity to study it. Observatories around the world had their instruments trained on this cosmic traveler as it swung past Earth at a safe distance, gathering data that would help scientists understand its composition, its structure, its origins. The plan was straightforward: track it precisely, measure its trajectory, predict where it would go next. But 3i Atlas exhibited unexpected behavior. Within days of passing Earth, something happened. Something shifted. The comet changed direction in a way that deviated from predictions, and suddenly, teams at NASA and observatories worldwide were recalculating their models, double-checking their data, trying to understand what force was acting on this visitor from interstellar space. This isn't the first time it's happened. Since we started tracking 3i Atlas, it's shown a pattern of unpredictability. Small course changes, tiny accelerations that shouldn't be there if gravity alone were guiding its path. But the December 26th confirmation brought renewed focus because it happened so soon after the close approach, during a period when we had more eyes on it than ever before. The timing matters, the magnitude matters, and the fact that it keeps happening matters most of all. Here's why this captures attention beyond the scientific community. We live in an age where we can predict planetary positions decades in advance, where we send spacecraft to distant worlds with pinpoint accuracy, where our understanding of orbital mechanics is so refined that we can land rovers on Mars within specific target zones. Yet here comes an object from beyond our solar system, and it keeps surprising us. It keeps deviating. It keeps reminding us that for all our technological advancement, the universe still holds phenomena we're only beginning to comprehend. So what's actually pushing it off course? What force is acting on this interstellar traveler that our models struggle to capture? And perhaps more importantly, what does this tell us about the nature of objects that wander between the stars? Hit the like button if you're tracking this cosmic mystery with us, and drop a comment telling me where you're watching from. Because right now, people all over this planet are looking up at the same sky, wondering about the same visitor, united by curiosity about what's happening out there in the darkness. We're all witnesses to this together, and what we're about to explore will change how you think about our place in a universe that's far stranger and more dynamic than most people realize. The answers are complex, but they're within reach. Let's begin with what has been observed throughout its passage through the inner solar system. December 19th, 2025. That's when 3i Atlas made its closest approach to Earth during this passage through our solar system. Observatories had been preparing for months, knowing this would be their best chance to gather detailed observations of an interstellar comet in motion. The flyby itself was uneventful in the best possible way. The comet passed at a safe distance, exactly where calculations suggested it should be at that moment. Instruments captured spectra, measured brightness, analyzed the light reflecting off its surface and streaming from its tail. Everything seemed to align with expectations. Scientists breathed easier, knowing the prediction models had worked for the approach phase. Then came the days that followed. As 3i Atlas continued on its outbound journey away from the inner solar system, astronomers kept watching. This is standard procedure with any comet, but especially with an interstellar visitor where every data point is precious. They were tracking its position against the background stars, measuring how fast it was moving, calculating its trajectory forward based on the gravitational influences of the sun and planets. The models took into account everything we know about orbital mechanics, the pull of solar gravity, the gentle tug of Jupiter's massive presence, even the subtle effects of smaller bodies. The predictions showed where 3i Atlas should be at any given time, where it should appear in the sky relative to distant background stars. Within days of the close approach, careful measurements revealed trajectory deviations. The position measurements coming from multiple observatories weren't matching the predicted trajectory. The comet was slightly off course. Not dramatically, not in a way that suggested anything dangerous or catastrophic, but enough that the deviation exceeded measurement error margins. When astronomers checked their calculations, verified their instruments, and compared notes across different observation sites, the conclusion became unavoidable. 3i Atlas had changed direction. Something was accelerating it in a way that gravity alone couldn't explain. This is where we need to pause and understand what trajectory deviation actually means in the context of space objects. When a comet or asteroid moves through the solar system, its path is determined primarily by gravity. The Sun's gravitational pull is the dominant force, keeping objects in predictable orbits or hyperbolic paths for interstellar visitors just passing through. We can calculate these trajectories with extraordinary precision because gravity follows laws we understand deeply. Isaac Newton gave us the foundational mathematics centuries ago, and Einstein refined it further with general relativity. If gravity were the only force at play, we could predict comet positions months or years in advance with minimal error. But comets aren't just inert rocks floating through space, they're active objects, especially when they get close to the Sun. The heat from sunlight warms their surfaces, causing frozen materials, ices of water, carbon monoxide, carbon dioxide, and other compounds, to sublimate directly from solid to gas. These gases escape from the comet's surface, forming the characteristic tail that makes comets visible and beautiful. And here's the critical part. When gas jets shoot out from one side of a rotating comet, they create a rocket effect. The escaping gas pushes against the comet, creating a small but measurable force that changes the object's velocity and trajectory. This phenomenon is called non-gravitational acceleration, and it's well documented in solar system comets. Scientists have been accounting for it in trajectory calculations for decades. The challenge with 3i Atlas, however, is that we don't know its surface in detail. We don't have maps showing which areas are rich in which types of ice, where the jets are likely to form, how the rotation brings different regions into sunlight. For comets that originate in our solar system and make regular passes near the Sun, astronomers can build these models over multiple observations. But 3i Atlas is making a single pass. It came from interstellar space, swung through our solar system once, and it's leaving forever. We're building the model in real time with limited data. The December 26th confirmation of trajectory change wasn't the first deviation observed with 3i Atlas. Since tracking began in earnest, scientists had noticed small discrepancies between predicted and observed positions. These earlier deviations prompted research teams to incorporate non-gravitational effects into their models. But even with those adjustments, the comet kept surprising them. Each new set of observations revealed behavior that required model refinement. It's like trying to predict the path of a runner through a forest when you can only see them intermittently through the trees, and the runner keeps changing speed and direction based on terrain you can't observe directly. What made the late December observation particularly significant was the timing and the data quality. Just days after the Earth flyby, when observation conditions were still excellent, and multiple facilities were actively tracking the comet, the deviation became impossible to attribute to measurement uncertainty. The numbers were solid, the position was off, and the magnitude of the deviation suggested that outgassing activity might be stronger or more asymmetric than earlier models had assumed. Picture the scene in astronomy communities during those days. Research teams comparing datasets, running simulations to see what level of outgassing would be required to produce the observed deviation, checking whether the amount of gas needed matched what spectroscopic observations were showing. It's detective work, piecing together clues from different types of evidence to build a coherent picture. Some teams focused on the trajectory math, calculating exactly how much force would be needed to push the comet off its predicted path by the observed amount. Others analyzed the spectral data, looking at the chemical signatures in the light from 3i Atlas to determine what gases were present and in what quantities. The consensus that emerged wasn't that 3i Atlas was doing something impossible. It was that this interstellar comet was exhibiting stronger and more complex outgassing behavior than the simplified models had captured. The fundamental explanation, that escaping gases were pushing it around, was sound. But the details of how, where, and when those gases were escaping required more sophisticated modelling. And here's where it gets truly interesting. Even with that consensus, scientists acknowledged that 3i Atlas was showing features that made it unusual even among objects with known outgassing. The trajectory deviation observed on December 26th wasn't just a simple push in one direction. The data suggested changes in both the velocity magnitude and the direction of travel, implying that outgassing jets weren't coming from a single spot in a steady stream. Instead, the comet's rotation was bringing different active areas into sunlight, creating a complex pattern of forces that varied over time. Think of it like a sprinkler that's spinning while water jets out at different angles. The net effect on the sprinkler's position depends on the timing and strength of each jet, and predicting that requires knowing the internal structure and rotation in detail. By the end of December, NASA and affiliated research teams had released updated trajectory predictions that incorporated higher estimates of non-gravitational acceleration. The new models fit the observations better, but they came with wider uncertainty margins looking forward. In other words, scientists could explain what had already happened, but predicting future positions became harder because the outgassing behavior wasn't following a simple, steady pattern. This is the reality of studying something we've never encountered before at this level of detail, an interstellar comet whose surface composition, internal structure, and rotation characteristics are all unknowns we're solving for simultaneously. So what was actually pushing 3I Atlas off its predicted course by late December? The answer, supported by multiple lines of evidence, pointed to outgassing. But that answer immediately raised new questions. Why was the outgassing so strong? What specific gases were involved? How was the comet's rotation creating the observed pattern of deviations? And most intriguingly, were there features about this interstellar visitor that made it fundamentally different from the comets that formed in our own solar system? Those questions take us deeper into the science, into the remarkable observations made by some of the most powerful instruments humanity has ever built, and into the heart of what makes 3I Atlas such a compelling subject of study. The December 26th trajectory change wasn't an endpoint. It was a doorway into understanding forces that operate on objects travelling between the stars. Let's talk about what's really happening on the surface of 3I Atlas as it moves through our solar system. The answer to the trajectory mystery lies in a process that sounds almost simple when you first hear it, but becomes beautifully complex when you understand the physics involved. Outgassing. It's the primary explanation for why this interstellar comet keeps deviating from purely gravitational predictions, and it's a phenomenon we've observed in countless comets before. But as with everything related to 3I Atlas, the details reveal something far more interesting than a textbook example. Here's how it works from the ground up. Comets are often described as dirty snowballs, which captures part of the truth but misses important nuances. They're mixtures of ice and rock, dust and frozen gases, accumulated from the materials present in whatever region of space they formed. For comets from our solar system, those materials came from the protoplanetary disk that eventually formed the Sun and planets. For an interstellar comet like 3I Atlas, those materials came from conditions around a different star entirely. In a molecular cloud or planetary system we'll probably never identify with certainty. When a comet is far from any star, cruising through the cold darkness of space, it's essentially inert. The surface is frozen solid, temperatures are near absolute zero and nothing is changing. But as it approaches a star, in this case our Sun, everything transforms. Sunlight carries energy. That energy, in the form of photons, hits the comet's surface and heats it up. Not uniformly, because comets rotate and have irregular shapes with varying compositions, but enough to raise temperatures above critical thresholds. And when you heat ice in the vacuum of space, it doesn't melt into liquid. It sublimates, transitioning directly from solid to gas. This is where the rocket effect comes into play. Imagine frozen carbon monoxide locked in the surface layers of the comet. As sunlight warms that region, the carbon monoxide molecules gain enough energy to break free from the solid matrix. They burst out as gas, escaping into space. But here's the critical part. Gases escaping from one side of an object in space create thrust, exactly like a rocket engine. Newton's third law applies perfectly here. For every action, there's an equal and opposite reaction. The gas molecules shooting away from the surface push back on the comet itself, changing its velocity ever so slightly. Now, if this were happening uniformly across the entire surface, the forces might balance out. But it's not uniform. Comets rotate, bringing different regions into sunlight at different times. Some areas might be rich in volatile ices that sublimate easily, while others are covered in dust or composed of more stable materials. The result is asymmetric outgassing, jets of gas erupting from specific locations, active when those locations face the sun, quiet when they rotate into shadow. Over hours and days, as the comet spins, these jets create a complex pattern of forces that add up to change the comet's trajectory in ways that pure gravity wouldn't predict. For 3I Atlas, observations have confirmed that outgassing is absolutely happening. We're not guessing or inferring from indirect evidence. We have direct spectroscopic data showing what gases are present in the material streaming away from the comet. The James Webb Space Telescope, with its extraordinary sensitivity to infrared light, captured detailed spectra that revealed the chemical fingerprints of carbon dioxide as the dominant outgassing species, with carbon monoxide also present. Carbon monoxide is particularly important because it's extremely volatile. It sublimates at very low temperatures compared to water ice. This means carbon monoxide-rich comets can start outgassing farther from the Sun than water-dominated comets, and they can produce stronger jets because the gas is under higher pressure as it escapes. In addition to carbon monoxide, observations detected carbon dioxide and water vapour in smaller quantities. Each of these molecules contributes to the overall outgassing activity, but carbon dioxide appears to be the primary driver for the non-gravitational acceleration observed in 3I Atlas, with carbon monoxide also contributing. The high carbon dioxide content is itself interesting because it suggests something about where and how this comet formed. In the coldest regions of space, far from stars, carbon monoxide is more likely to condense and be incorporated into icy bodies. Finding carbon dioxide as the major volatile in an interstellar comet tells us that 3I Atlas likely originated in a very cold environment, possibly ejected from an outer planetary system or formed in interstellar space itself. The amount of gas being released is staggering when you do the math, even though we're talking about effects that change the comet's velocity by small amounts. Scientists estimate that 3I Atlas is losing mass continuously as it travels through the inner solar system, shedding gases and dust particles that form the tail visible in telescopes. The total mass loss over the course of its passage near the Sun amounts to a significant fraction of the comet's surface layers. It's literally evaporating as we watch, sacrificing material to space in exchange for the spectacular display of activity. Now, here's where scientific honesty becomes important. Outgassing explains the trajectory deviations. The physics is well understood, the observations confirm gases are escaping, and the magnitude of the non-gravitational acceleration is consistent with what we'd expect from a comet rich in volatile ices. This isn't speculation. This is established science backed by multiple independent lines of evidence. Research teams have published papers detailing the outgassing rates, the composition of the escaping gases, and the models that successfully account for the observed trajectory changes when outgassing is included. But, and this is where 3I Atlas remains fascinating, the specific behaviour of this comet pushes the boundaries of what we've seen before. The strength of the outgassing, the particular mix of volatiles, and the pattern of trajectory changes all mark this as an unusual case even within the framework of understood physics. It's like seeing a perfectly legal move in chess that you've never witnessed in thousands of games. The rules allow it. The move makes sense, but it's rare enough to make you pay attention. The rotation of 3I Atlas plays a crucial role in how the outgassing affects its trajectory. Every comet rotates, tumbling through space as it orbits. For solar system comets that we've studied extensively, astronomers have often determined rotation periods, axis orientations, and how those factors influence outgassing patterns. For 3I Atlas, we're still building that picture. Early observations suggested a rotation period measured in hours, but the exact spin axis orientation remained uncertain for some time. This matters enormously because the direction of the spin axis determines which parts of the surface get heated at which points in the orbit. Imagine a comet rotating like a top, with its spin axis pointed toward the Sun. In that configuration, one region near the pole would be constantly illuminated, potentially creating a steady jet of outgassing from that area. Now imagine a different orientation where the spin axis is perpendicular to the Sun direction, causing the comet to tumble end over end with different hemispheres cycling through day and night. That configuration would create varying outgassing patterns as different regions heat up and cool down. The trajectory effects from these two scenarios would be dramatically different. For 3I Atlas, evidence emerged that its rotation axis might be aligned in a way that's statistically unusual compared to other comets. This doesn't mean impossible or unphysical, but it does mean that if you randomly picked comets from a population and measured their spin axes, you wouldn't expect to see this particular orientation very often. That rarity adds to the overall picture of 3I Atlas as an object that, while behaving according to known laws of physics, represents an outlier in the distribution of observed properties. The outgassing also creates visual phenomena that astronomers have documented in remarkable detail. Beyond just the main tail pointing generally away from the Sun, 3I Atlas developed what's called an antitail, a tail-like feature that appears to point toward the Sun, seemingly defying the logic of how comet tails form. Antitails aren't actually defying physics, They're perspective effects combined with dust particle dynamics. When large dust particles are released from the comet, they don't immediately fly away from the Sun like the gas does. Instead, they follow orbits that are only slightly perturbed from the comet's orbit, creating a trail of material along the comet's path. From certain viewing angles, this trail can appear to extend toward the Sun, creating the antitail appearance. What made the 3I Atlas antitail particularly noteworthy was that observations showed it wobbling, changing shape and direction over short timescales. This wobbling was documented around December 22nd, just before the trajectory deviation confirmation. The wobbling antitail suggests that the outgassing isn't steady, but instead pulsating or varying as different active regions rotate in and out of sunlight. It's like watching a garden hose being waved around while water flows through it. The stream changes direction based on how the nozzle is moving. All of this complexity, the carbon dioxide dominance, the rotation effects, the wobbling antitail, the trajectory deviations, stems from outgassing. It's a single underlying phenomenon manifesting in multiple observable ways, each piece of evidence reinforcing the overall picture. When scientists say they understand why 3I Atlas changed course, they're not guessing. They're pointing to a well-documented physical process with observational confirmation from multiple instruments and techniques. Yet understanding the mechanism doesn't mean we can predict every detail with perfect accuracy. The challenge remains that we don't have a complete map of the comet's surface composition or a perfect model of its rotation state. We're refining those models with each new observation, but there's inherent uncertainty when studying an object we'll only see once, an object that came from conditions we've never directly sampled. The outgassing explanation is correct, but the specific implementation of that explanation in predictive models continues to evolve as more data becomes available. This brings us to a deeper question that lingers even after accepting the outgassing explanation. If this is just a comet behaving like comets do, releasing gases as it's heated by the Sun, why does 3I Atlas feel so different? Why do astronomers speak about it with a mixture of scientific confidence and genuine curiosity? The answer lies not in what the comet is doing, but in how rare and extreme the specifics turn out to be. Outgassing explains the mechanism, but the magnitude, timing, and characteristics of that outgassing place 3I Atlas in a category we've rarely encountered before. Understanding what makes 3I Atlas unusual requires stepping back from the individual observations and looking at the broader context of comet science and interstellar object detection. Yes, the outgassing explanation accounts for the trajectory changes. Yes, the physics is well established, but within that framework of understood phenomena, 3I Atlas exhibits a collection of characteristics that, when taken together, mark it as exceptional. It's the difference between seeing rain, which is common and understood, and seeing rain in a pattern or intensity that makes meteorologists take notice even though they know exactly how rain forms. Start with the wobbling antitail observed in late December. Antitails themselves aren't extraordinarily rare. They've been documented in various comets over the years, when geometry and dust dynamics align just right. What caught attention with 3I Atlas was the dynamic nature of that antitail, the visible changes happening over short timescales. This suggests that the dust release from the comet's surface wasn't steady but instead highly variable, with bursts of activity creating clumps and structures in the dust trail that rotated into and out of our line of sight. The variability points to active regions on the surface that aren't uniformly distributed. Imagine a comet where one hemisphere has multiple jets of gas and dust erupting from specific fissures or exposed ice patches, while the other hemisphere is relatively quiet, covered in a non-volatile crust. As the comet rotates, those active regions would turn on and off from our perspective, creating the pulsating appearance in observations. This level of surface heterogeneity isn't unheard of, but documenting it so clearly in an interstellar object adds valuable data to our very limited sample of what these visitors look like. Then there's the rotation axis alignment, which multiple research teams have attempted to characterize through analysis of the light variations and outgassing patterns. Early findings suggested that the spin axis might be oriented in a way that places it in the tail of statistical distributions, meaning if you measured spin axes for a large population of comets, this particular orientation would show up less frequently than others. Why does orientation matter? Because it affects how sunlight interacts with the surface over the course of the orbit, which in turn determines the heating patterns and outgassing distribution. A comet with its spin axis perpendicular to its orbital plane will experience very different heating than one with an axis aligned with the orbital plane. The former might have more uniform heating across latitudes as it tumbles, while the latter might have polar regions that are preferentially heated or cooled. For 3I Atlas, The orientation appears to fall into a configuration that enhances certain outgassing behaviors, potentially contributing to the strength of the non-gravitational acceleration observed. It's not that this orientation is forbidden by physics, it's simply less common in the observed population, making 3I Atlas a valuable case study for understanding the full range of possible comet behaviors. Now, layer in the context of interstellar objects. As of now, we've confirmed only 3 objects from beyond our solar system. Oumuamua, discovered in 2017, 2I Borisov, discovered in 2019, and 3I Atlas. 3 objects total in the history of astronomy, where we can confidently say they originated elsewhere and are just passing through. This means our sample size for understanding what's normal for interstellar objects is absurdly small. We simply don't have enough data points to draw broad conclusions about typical versus unusual characteristics. Oumuamua famously exhibited non-gravitational acceleration that sparked intense debate precisely because it showed no visible outgassing, no tail, no coma, no obvious comet-like activity, yet still deviated from a purely gravitational trajectory. The leading explanation involved outgassing of materials we couldn't detect optically, possibly hydrogen molecules that don't emit light in visible wavelengths. But the lack of traditional comet features made Oumuamua a puzzle that remains incompletely solved, and it opened up discussions about whether interstellar objects might be fundamentally different from solar system objects. 2I Borisov, the second confirmed interstellar visitor, looked much more like a traditional comet. It had a visible coma and tail, showed clear signs of outgassing, and behaved in ways that matched solar system comets fairly well. Its composition was similar to what we see in our own comets, suggesting that comet formation processes might be universal across different stellar environments. Borisov eased some of the tension created by Oumuamua's weirdness, providing reassurance that not all interstellar objects are bizarre outliers. 3I Atlas falls somewhere between those two cases in terms of how it fits expectations. It clearly shows comet-like activity, unlike Oumuamua. It has outgassing that's directly observable and measurable, providing straightforward explanations for trajectory deviations. In that sense, it's less mysterious than Oumuamua. But the specific characteristics, the strength of the carbon dioxide outgassing, the wobbling antitail, the rotation alignment, the magnitude of trajectory changes, push it toward the unusual end of the spectrum even within the comet category. It's behaving like a comet, but like an extreme or rare type of comet. Avi Loeb, the astronomer who's been vocal about considering unconventional explanations for unusual objects, has commented that some features of 3I Atlas are extremely rare in the comet populations we've studied extensively. This doesn't mean he's claiming it's artificial, or that it defies physics. Context matters enormously with such statements. What it means is that among the thousands of solar system comets observed over centuries, the combination of traits seen in 3I Atlas would place it in a small minority. Rare doesn't equal impossible, it equals interesting and worthy of detailed study. The honest scientific position, which reflects the consensus among researchers actively studying 3I Atlas, is that this object is unusual but explainable. Every observed feature has a physical mechanism behind it. Outgassing explains trajectory changes. Carbon dioxide dominance explains the strength and distance of activity. Rotation and surface heterogeneity explain variability. But the specific combination and intensity of these features make 3I Atlas a standout case, something worth documenting thoroughly, because it expands our understanding of the range of behaviors real objects can exhibit. This is how science progresses with rare phenomena. You don't dismiss something as uninteresting just because it fits within known physics, and you don't leap to extraordinary conclusions just because something is unusual. You document it carefully, you model it rigorously, and you let the data inform your understanding. 3I Atlas is doing exactly what it should do as an icy body heated by the sun, but it's doing so with characteristics that challenge our models to be more sophisticated, that expose gaps in our predictive capabilities, and that remind us how much we still don't know about the population of objects drifting between stars. Consider also what we're not seeing. We're not seeing erratic movements that violate conservation of momentum. We're not seeing accelerations that require energy sources beyond solar heating and volatile sublimation. We're not detecting signals or behaviors that demand new physics. Every measurement taken by instruments ranging from ground-based telescopes to space-based observatories like the James Webb Space Telescope points to natural, physical processes operating exactly as the laws of nature dictate. The comet isn't defying those laws. It's exhibiting a rare configuration of properties allowed by those laws. The rarity itself teaches us something valuable. It tells us that interstellar space is diverse. that comets formed around other stars can have compositions and structures that differ from the average in our solar system, and that when we finally begin detecting interstellar objects routinely, we should expect variety. We should expect some visitors to look familiar, and others to surprise us with extreme values of otherwise normal properties. 3i Atlas is preparing us for that future by showing what unusual but natural looks like. There's also a practical dimension to why unusual matters. When astronomers develop models to predict where 3i Atlas will be in the future, critical for planning observations or understanding its long-term path, they need to account for these unusual characteristics. Standard comet models that work well for typical solar system comets don't capture 3i Atlas's behavior accurately without significant adjustments. The strength of outgassing, the timing of activity, the directional components of the non-gravitational forces, all of these require custom modeling informed by ongoing observations. That's scientifically challenging and rewarding, pushing researchers to refine techniques and develop more flexible frameworks. So when we say 3i Atlas is unusual, we're making a specific claim grounded in comparative analysis. It's unusual relative to the thousands of solar system comets we've observed. It's unusual relative to the very small sample of interstellar objects detected so far. It's unusual in ways that are measurable and documentable, not in ways that require invoking unknowns or abandoning established physics. And that's precisely what makes it scientifically valuable. Unusual cases stress test our understanding, revealing where our models are robust and where they need improvement. The path forward for understanding 3i Atlas involves continued observation as long as it remains bright enough to detect, integration of all available data into comprehensive models, and honest assessment of what we know versus what we're still figuring out. The unusual characteristics aren't evidence of anything beyond natural processes taken to interesting extremes, but they're evidence that the universe routinely produces phenomena that sit at the edges of our experience, expanding what we consider possible within the realm of the natural. As 3i Atlas continues outbound, leaving the inner solar system behind, its unusual nature ensures it will remain a subject of study and discussion for years to come. But studying it means tracking it, and tracking it means knowing where it is right now and where it's going next. Right now, as you're watching this, 3i Atlas is moving through the constellation Leo, visible primarily from the southern hemisphere as it continues its outbound journey away from the Sun and Earth. Its brightness has faded significantly since the December flyby. Comets brighten as they approach the Sun due to increased activity, and they dim as they recede into colder regions of space where outgassing decreases. For professional observatories with large telescopes, it remains a viable target for monitoring, but for casual stargazers, the window of easy visibility has largely closed. This is the nature of comet observation, a brief period of prominence followed by a gradual fade into dimness as the object retreats. The fading isn't just about distance, though distance plays a role. It's primarily about activity level. As 3i Atlas moves farther from the Sun, the sunlight intensity decreases, which means less energy hitting the comet's surface to drive sublimation. The outgassing that created such dramatic effects in late December is now slowing down. Carbon monoxide, despite being highly volatile, still requires a minimum level of solar heating to sublimate actively. As that heating drops below critical thresholds, the jets weaken, the coma shrinks, and the overall brightness decreases. The comet is returning to a more dormant state, though not yet completely inert. Observers equipped with moderate-sized amateur telescopes in good dark sky locations can still potentially spot 3i Atlas if they know exactly where to look and have up-to-date ephemerides, tables showing predicted positions. But it's no longer the relatively easy target it was during the approach and close flyby. This gradual dimming marks the transition from peak observation opportunity to the long-term monitoring phase where only dedicated facilities with sensitive instruments will track it. And track it they will, because the story of 3i Atlas isn't over. There's another chapter coming, one that has astronomers eagerly anticipating what new data it might provide. March 2026. That's the next milestone on 3i Atlas's journey through our solar system, a close approach to Jupiter. Not a collision, not even a particularly close pass by planetary standards, but close enough that Jupiter's massive gravitational field will interact with the comet's trajectory in measurable ways. This interaction is scientifically valuable for several reasons, all of which relate to refining our understanding of the comet's motion and testing our models under new conditions. When a small object like a comet passes by a massive object like Jupiter, the planet's gravity bends the comet's path. The amount of bending depends on how close the approach is, how fast the comet is moving, and the exact trajectory geometry. If we know Jupiter's mass and position with high precision, and we absolutely do, then by observing how 3I Atlas's path changes during the encounter. We can test whether our models of the comet's trajectory before the encounter were accurate. It's like having a calibration point, a place where well-understood forces dominate and allow us to check our work. For 3I Atlas, the Jupiter encounter will also help clarify how much non-gravitational acceleration is still affecting it by that point in its journey. If the comet is still actively outgassing in March, that will continue to influence its path in ways that compete with Jupiter's gravitational pull. By carefully measuring the trajectory change during the Jupiter encounter and comparing it to predictions that include only gravity, scientists can assess whether residual outgassing is still significant or whether the comet has become inactive enough that gravity alone governs its motion. That distinction matters for predicting where 3I Atlas will be in the distant future as it leaves our solar system entirely. Beyond Jupiter, the path is straightforward in principle if not in perfect detail. 3I Atlas is on a hyperbolic trajectory, which in orbital mechanics terms means it has enough velocity to escape the Sun's gravitational pull. It's not bound to our solar system, it came from interstellar space, swung through the inner system, and it's heading back out into the void. The hyperbolic trajectory ensures that as long as nothing catastrophic happens, like a collision, which is astronomically unlikely, the comet will eventually pass beyond the influence of the Sun's gravity and return to interstellar space. The timeline for that departure depends on how you define the edge of the solar system. If you mean the region where the Sun's gravity no longer dominates over other stars' gravity, that's many thousands of astronomical units away, and 3I Atlas will take tens of thousands of years to reach those distances. If you mean the heliopause, where the solar wind gives way to interstellar medium, that's much closer, roughly 100 astronomical units, and 3I Atlas will cross that boundary much sooner. Within a few years to a decade, depending on exact velocity after all the trajectory adjustments, it will pass beyond the outermost reaches of our planetary system and become an interstellar traveller once again. Think about what that means. This object, which captured attention worldwide for a few months as it passed through our neighbourhood, will spend the next millions or billions of years drifting through the galaxy. It might never encounter another star closely. It might pass through molecular clouds, accumulating more material on its surface. It might eventually be perturbed by gravitational interactions with other interstellar objects, or the collective pull of the galaxy's structure, altering its course in ways we'll never observe. It came from somewhere unknown, visited us briefly, and now it returns to that unknown. There's a poignancy to that realization. Every observation we make now is our only chance to understand this particular visitor. There are no return trips, no follow-up missions decades later when technology improves. The data we gather during this single pass is all we'll ever have for 3I Atlas specifically. That's why astronomers are making the most of it, why every observation is carefully recorded and analysed, why even as it fades from view there are instruments still pointed in its direction capturing whatever light they can. The Jupiter flyby in March represents one of the last major opportunities for significant new data before 3I Atlas becomes too faint for all but the most powerful telescopes to track. After Jupiter, as the comet continues outbound and cools further, it will become progressively harder to observe. Activity will drop to near zero, eliminating the brightness boost that outgassing provides. The object will be reflecting sunlight only, and as it gets farther away, the reflected light dims according to inverse square law. Double the distance, 1/4 the brightness. Within months after the Jupiter encounter, 3I Atlas will likely drop below the detection threshold for most facilities. But before it fades completely, that March encounter offers a final window to gather information. Observatories are already planning their observation campaigns, coordinating to get as much coverage as possible during the close approach. They'll measure the trajectory with high precision, watching for any deviations that might tell us whether the comet is still outgassing at low levels. They'll capture final spectra if the object is still bright enough for spectroscopy, documenting any changes in composition or activity level, and they'll use the Jupiter encounter as a natural experiment, watching how a massive planet's gravity sculpts the path of an interstellar visitor. There's something deeply human about this desire to watch until the very end. We could mathematically project where 3I Atlas will go after the Jupiter encounter based on current data and call it done. The additional observations after March won't fundamentally change the broad story of what this comet is or where it came from, but we watch anyway, driven by curiosity, by the knowledge that every data point improves our models just a little, and by the awareness that we're witnessing something rare that deserves our full attention for as long as we can maintain it. As 3I Atlas dims and recedes, becoming first a faint smudge in professional images and then just a calculated position on star charts, its legacy will remain. The observations collected during its passage will feed into databases used by researchers for years. The trajectory deviations will become case studies in modelling non-gravitational forces. The compositional data will inform theories about how comets form in different stellar environments. And the simple fact of its detection and successful tracking will boost confidence that we're developing the capability to spot and study future interstellar visitors. Because 3i Atlas won't be the last. Current estimates suggest we should be able to detect 1 or 2 interstellar objects per year with existing survey telescopes once we know what to look for. The legacy survey of space and time, set to begin operations soon, will dramatically increase our sky coverage and sensitivity, likely revealing interstellar visitors with much greater frequency. Each one will be a new opportunity to learn, to test our understanding against objects formed under alien conditions, to build a catalogue of what's out there in the space between stars. So while 3i Atlas's time in the spotlight is waning, its significance extends far beyond these months of active observation. It's teaching us how to study objects we'll only see once. It's showing us what unusual but natural looks like. And it's preparing us for the era, not far away, when interstellar visitors are routine detections rather than rare surprises. That future transforms these objects from isolated curiosities into a new population available for systematic study, and 3i Atlas is paving the way for that transformation. But why should any of this matter beyond the community of astronomers and space enthusiasts tracking these developments? Why should the general public care about an icy rock from another star system changing its trajectory slightly as it passes through our neighbourhood? The answer to that question requires shifting perspective from the specific object to what it represents about our place in the universe and our growing capabilities to understand that universe. Every time an interstellar object enters our solar system and we successfully detect and study it, we're gaining information that's literally impossible to obtain any other way. We cannot send spacecraft to other star systems with current technology. The distances are too vast, the travel times measured in generations or millennia, even with hypothetical propulsion systems far beyond what we've built. We cannot point telescopes at distant solar systems and directly observe their comets in detail. They're too small and too faint across interstellar distances. But when those comets come to us, passing through our neighbourhood, we suddenly have access to material formed under conditions we otherwise could never sample. It's like having meteorites delivered to our doorstep from stellar systems we'll never visit. 3i Atlas represents exactly that opportunity. It formed somewhere else, around another star or in interstellar space itself, incorporating materials from that environment. By studying its composition, the mix of ices, the ratio of carbon monoxide to other volatiles, the dust properties, we're getting a direct sample of what conditions were like where it formed. That's extraordinary. Typically, to understand the composition of distant regions, we rely on spectroscopy of starlight or observations of nebulae, which give us bulk properties of gas and dust, but not the specific outcomes of accretion and freezing processes that create small bodies. The dominance of carbon monoxide in 3i Atlas's outgassing tells us something important. It suggests formation in an extremely cold environment where carbon monoxide could condense and remain stable, which points to either the outer reaches of a planetary system or true interstellar space. This is different from the composition profile of most solar system comets, where water ice tends to be more dominant. That difference isn't random, it reflects temperature gradients in the regions where these objects accumulated their material. By cataloguing these differences across multiple interstellar visitors, we build a picture of the diversity of comet-forming environments in the galaxy. This matters for understanding planet formation generally. Comets are leftover building blocks from the process that creates planets. They're the scraps, the material that didn't get incorporated into larger bodies, preserved in cold storage for billions of years. When we study comets from our own solar system, we learn about conditions in the protoplanetary disk around the Sun. When we study interstellar comets, we learn about conditions in other protoplanetary disks, or about interstellar material that never belonged to a specific star. Comparing these populations reveals whether planet formation is a universal process with minor variations, or whether there's significant diversity in how planetary systems assemble. Beyond composition, the behaviour of 3i Atlas during its passage teaches us about comet physics under conditions we hadn't directly tested before. The strength of its outgassing, the rotation effects, the trajectory deviations, all of these are data points that test our models of how icy bodies respond to solar heating. Models developed based on solar system comets might have hidden assumptions or parameters tuned to match the specific objects we've observed most extensively. When you apply those models to an object from a different population, discrepancies reveal where the assumptions break down or where the parameter space needs to be expanded. This is how scientific understanding becomes more robust. You test your theories against diverse cases, not just the ones that fit easily. 3I-Atlas challenges Comet models by exhibiting strong carbon monoxide outgassing and unusual rotation, forcing scientists to make sure their frameworks can handle that combination. The result is models that are more general, more flexible, and more likely to work correctly when applied to future discoveries. It's unglamorous work in some sense, refining equations and adjusting parameters, but it's essential for building knowledge that's genuinely predictive, rather than just descriptive of what we've already seen. There's also a planetary defense dimension to tracking interstellar objects, though it's more about capability development than immediate threat assessment. 3I-Atlas wasn't on a collision course with Earth, and the probability of an interstellar object actually hitting us is vanishingly small given the vastness of space. But the ability to detect objects entering the solar system from unusual trajectories, calculate their paths accurately despite non-gravitational forces, and monitor them continuously as they move through our neighbourhood, all of that builds institutional capacity and technical expertise that applies to planetary defense more broadly. If we can track an interstellar comet with unpredictable outgassing, and still pin down its trajectory well enough to know it's safe, we're demonstrating capabilities that would be crucial if we ever did detect an object on a hazardous path. The techniques developed to model 3I-Atlas's non-gravitational acceleration, the coordination between observatories to maintain continuous coverage, the rapid analysis and model updating as new data comes in, these are all transferable skills that strengthen our overall ability to track near-Earth objects regardless of their origin. Then there's the technological milestone that detecting 3I-Atlas at all represents. A few decades ago, we likely wouldn't have spotted it. Survey telescopes weren't as sophisticated, detection algorithms weren't as refined, and the infrastructure for rapid follow-up observations wasn't as developed. The fact that we now routinely detect interstellar objects within months of their arrival in the inner solar system, sometimes even before they reach peak brightness, reflects massive improvements in observational astronomy. We're living through a transition from an era where such objects were theoretical possibilities to an era where they're expected detections. That transition matters because it opens up interstellar objects as a field of study rather than isolated curiosities. With a sample size of 3 confirmed objects, Oumuamua, 2I, Borisov, 3I-Atlas, we can start to ask population-level questions. What's the typical composition? What's the range of sizes? How do formation environments correlate with physical properties? These questions were unanswerable when we had 0 or 1 example. With each new detection, the statistical power grows, and the ability to draw general conclusions improves. Looking ahead, the next generation of survey telescopes will dramatically increase the detection rate. Current estimates suggest that once facilities like the Vera C. Rubin Observatory become fully operational, we might detect several interstellar objects per year instead of 1 every few years. That would transform the field within a decade, building a catalogue large enough for meaningful statistical analysis. 3I-Atlas is part of that early phase, where each object is still newsworthy individually, but it's paving the way for a future where these visitors are routine enough to study systematically. There's also the origin question, which remains tantalizing and largely unanswered for 3I-Atlas specifically. Where did it come from? Can we trace its trajectory backward and identify a likely source star? The challenge is that interstellar space is vast and stellar motions over millions of years scramble trajectories. An object that's currently entering our solar system from a particular direction might have been ejected from a star system that's now in a completely different part of the sky because both the Sun and that star have moved significantly in the intervening time. Researchers have attempted to backtrack 3I-Atlas's path through the galaxy, using the best available trajectory data and models of galactic gravitational potential. These studies can narrow down possibilities, identifying regions of the sky where the comet's past trajectory intersects with known star-forming regions or stellar associations, but they rarely produce definitive answers. The uncertainties in the trajectory, especially given the non-gravitational forces at play, propagate backward in time, creating wider and wider cones of possibility for where the object originated. Still, even probabilistic statements about origin are valuable. Knowing that 3I-Atlas likely came from a cold carbon monoxiduric environment, possibly associated with stellar formation regions that were active millions or billions of years ago, constrains the scenarios for how it formed and was ejected. That information feeds into models of planetary system dynamics, which predict that countless comets are ejected into interstellar space during the chaotic early phases of planet formation. 3i Atlas is likely one of those ejected bodies, a cast-off from some distant planetary system's youth, now wandering the galaxy until chance brought it close enough to our sun to wake it from dormancy. The philosophical dimension shouldn't be ignored either. We live in a time when we can detect and study visitors from other star systems. Think about what that means for our perspective. For all of human history until the 21st century, the only objects we could study in detail were from our own solar system, or electromagnetic radiation from distant sources. Now we're directly observing material from other stellar systems, holding conversations about its composition and behavior, treating it as a new category of object available for investigation. That's a profound expansion of what's accessible to science. 3i Atlas reminds us that our solar system isn't isolated. It exists in a galactic context where material flows between stars, where objects formed in one system can end up in another, where the space between stars isn't empty, but populated with wanderers carrying information about their origins. This connectivity, this exchange of material across vast distances, has implications for everything from the spread of organic molecules to the possibility of panspermia. The hypothesis that life, or its precursors, might be distributed through space on comets and asteroids. We're not ready to make grand claims about life based on 3i Atlas observations. There's no evidence suggesting this comet carries biological material, but the broader point stands. Interstellar objects are mechanisms for exchanging material between planetary systems, and over billions of years, that exchange could have significant consequences. Every interstellar visitor we study deepens our understanding of how that exchange works, what materials are being transported, and what conditions they experience during their journeys. So when we talk about why 3i Atlas matters, we're talking about multiple layers of significance. It matters for what it teaches us about comet composition and behavior. It matters for testing and refining our theoretical models. It matters for developing observational and analytical capabilities that apply to planetary defense and solar system surveying. It matters for building a population-level understanding of interstellar objects. And it matters for expanding our perspective on how our solar system fits into the larger galactic ecosystem. Each layer of significance reinforces the others, creating a compelling case that studying this object is time and resources well spent. But none of this exists in a vacuum separate from public discourse. As news about 3i Atlas spread through media channels and social platforms, various narratives emerged, some grounded in the actual science, and others veering into speculation or misinformation. Addressing those narratives directly is important, because public understanding of science depends on distinguishing what we actually know from what makes for compelling clickbait. Let's be completely clear about something from the start. 3i Atlas is not on a collision course with Earth. It never was. At its closest approach on December 19th, it passed at a safe distance of over 160 million miles, posing zero threat. NASA, the organization responsible for tracking near-Earth objects and assessing impact risks, confirmed explicitly that there was no danger. The trajectory change observed on December 26 did not alter that fact. The comet is moving away from us, heading outbound toward the outer solar system and eventually into interstellar space. There is no scenario consistent with the observational data where 3i Atlas comes back to threaten Earth. Yet if you've spent time on social media or certain corners of the internet, you might have encountered claims suggesting otherwise. Headlines designed to generate clicks and engagement sometimes phrase things in ways that create alarm, even when the underlying facts don't support it. A trajectory change can sound ominous if context is removed, if the fact that such changes were expected and understood isn't mentioned, if the reader isn't told that the change moved the comet farther away, not closer. This is how misinformation spreads, not always through outright falsehoods, but through selective presentation of information designed to trigger emotional responses. The algorithm-driven nature of modern content distribution amplifies this problem. Platforms prioritize engagement, and fear or surprise generates engagement more reliably than calm explanation. A headline saying "Comet changes course unexpectedly" will get more clicks than "Comet exhibits predicted outgassing behavior." The former sounds mysterious and potentially threatening. The latter sounds like a resolved scientific question, which doesn't trigger the same urgency to click and share. Content creators know this, and some prioritize maximizing views over accurately representing the science. We have to be honest about the ecosystem we're operating in. Information doesn't flow purely based on accuracy or importance. It flows based on what captures attention, and attention is often captured by implying threat or mystery. For 3i Atlas, that meant a flurry of misleading content suggesting the comet was behaving in unexplainable ways, that its trajectory change was unprecedented, that scientists were baffled or concerned in ways they simply aren't. Those narratives were more engaging than the truth, which is that scientists observed expected behavior with some unusual characteristics and successfully explained it with established physics. Another common thread in misinformation around interstellar objects involves speculation about artificial origins. This particular strain of misleading content tends to name-drop scientists like Avi Loeb, who has advocated for taking seriously the possibility that some unusual objects might be artifacts rather than natural phenomena. However, there's a critical distinction between Loeb's actual positions and how they're represented in sensational content. Loeb has said we should be open to considering all possibilities when faced with truly anomalous data, and he's specifically mentioned that certain features of interstellar objects could hypothetically be consistent with artificial origins if natural explanations fail. But, and this is where context matters enormously, Loeb has not claimed that 3I Atlas is artificial. He's commented that some of its features are rare, which is true. He's advocated for careful study, which is appropriate, but rare doesn't mean artificial, and advocating for open-minded investigation doesn't mean rejecting natural explanations that fit the data. The scientific position on 3I Atlas is clear. Outgassing explains the trajectory changes, the composition is consistent with natural comet formation, and every observation aligns with an icy body from another star system behaving exactly as physics predicts. The alien technology speculation fundamentally misunderstands what makes something truly anomalous in a scientific sense. If 3I Atlas were exhibiting behavior that violated known physics, accelerations without corresponding mass loss, trajectory changes without observable force sources, energy signatures that didn't match thermal processes, then extraordinary explanations would be on the table, but none of those conditions are met. Every measurement confirms natural processes. The trajectory changes match the scale expected from outgassing. The composition matches what forms in cold environments. The rotation and activity patterns are unusual within observed distributions but not outside the realm of natural possibility. Distinguishing between unexplained within our current limited models and unexplainable by known physics is crucial. When scientists say they're working to refine models to capture 3I Atlas's behavior more accurately, they're not saying the behavior defies explanation. They're saying the first-order approximations need adjustment to account for specific characteristics like strong carbon monoxide outgassing or particular rotation configurations. That's normal scientific refinement, not evidence of mystery beyond natural phenomena. The collision course rumours, the artificial origin speculation, and various other misleading claims share a common trait. They're more interesting to many people than accurate but less dramatic truths. There's a psychological pull toward mystery and threat that content exploiting those angles can leverage. Understanding that pull is important for developing resistance to misinformation. When you encounter a claim that sounds alarming or extraordinarily unusual, the first question should be, what's the source, and what do authoritative institutions actually say? For 3I Atlas, authoritative sources include NASA, the European Space Agency, peer-reviewed publications in astronomy journals, and statements from observatories directly involved in tracking the comet. Those sources consistently present a picture of a well-understood object, exhibiting natural behavior with some unusual characteristics. They don't support collision fears or artificial origin theories. When there's a disconnect between what authoritative sources say and what viral content claims, trust the sources with institutional credibility and transparent methodology over anonymous social media posts or clickbait articles. This doesn't mean you should blindly trust any authority or never question official narratives. Healthy skepticism is valuable, but healthy skepticism means demanding evidence and reasoning, checking multiple reliable sources, and updating beliefs based on the weight of evidence. It doesn't mean defaulting to the most dramatic interpretation or assuming that if something is unusual, it must be extraordinary in ways that defy natural explanation. The scientific community is actually quite good at acknowledging genuine mysteries. When Oumuamua was discovered and showed non-gravitational acceleration without obvious outgassing, astronomers openly discussed the puzzle and proposed various hypotheses, including some unconventional ones. They didn't try to force a premature explanation. They said, "This is unusual, we're not sure which explanation is correct, more data would help." That's the appropriate response to genuine anomaly. For 3I Atlas, the response has been different because the data supports a clear explanation. The scientific community is confident about the outgassing mechanism precisely because the evidence strongly points to it. One way to protect yourself against misinformation is to pay attention to what's not being said in sensational content. If a headline emphasizes mystery, check whether the article mentions that scientists have proposed explanations and supporting evidence. If a video implies threat, check whether official safety assessments are mentioned. Often, misleading content achieves its effect through omission rather than outright lies, leaving out the context that would make the situation less dramatic and therefore less engaging. Another protective factor is understanding base rates. How often do comets actually threaten Earth? Extremely rarely, and when potentially hazardous objects are detected, there are established protocols for public communication. How often have we detected confirmed artificial objects from other civilizations? Never in all of human history. Given those base rates, claims that any particular comet is a collision threat or an alien spacecraft should require extraordinary evidence to take seriously. For 3I Atlas, that extraordinary evidence doesn't exist. What exists is ordinary evidence of a natural comet behaving naturally. The misinformation problem matters beyond just correcting false claims about a specific comet. It matters because public understanding of science depends on being able to distinguish reliable information from noise. When misleading content spreads widely, it creates confusion that makes people less able to engage meaningfully with actual scientific developments. It breeds cynicism about expertise when people feel they've been misled, even if the actual scientific community wasn't the source of misleading claims. And it can create real-world consequences when misinformation influences decisions or policy. For 3I Atlas specifically, the stakes of misinformation are relatively low. It's not as though false beliefs about this comet will cause major policy errors or individual harm, but the habits of mind, the patterns of how people evaluate information, those generalize to contexts where stakes are higher. Building strong information literacy around a topic like interstellar comets helps develop skills that apply when evaluating claims about health, technology, environmental issues, or any other area where science informs public understanding. So the corrective message is straightforward. 3. IATLAS is not a threat. It is not mysterious in ways that defy natural explanation, and scientists understand what's happening with it. The trajectory changes are expected and explained. The unusual characteristics are interesting scientifically, but don't require invoking anything beyond well-established physics. And the path forward involves continued observation and modelling to refine our understanding of details, not puzzlement about fundamental mechanisms. With that foundation of accurate understanding established and common misconceptions addressed, we can turn to what genuinely remains mysterious about 3I Atlas. Not in a sensational sense, but in the sense of open scientific questions that research ongoing and future observations might help answer. The real mystery surrounding 3I Atlas isn't whether it defies physics or poses hidden dangers. The real mystery is in the details, in the specific questions that remain partially unanswered even after we understand the general mechanisms at play. These are the questions that drive ongoing research, that motivate continued observation campaigns, and that will likely occupy scientists analysing 3I Atlas data for years after the comet itself has faded from view. They're questions about the nature of this particular object and what it reveals about the population it represents. Start with surface composition and structure. We know from spectroscopic observations that carbon monoxide is the dominant volatile driving outgassing, with carbon dioxide and water present in smaller amounts. But that's a bulk measurement of what's escaping into space. It doesn't tell us about the detailed surface map, which regions are rich in which materials, where the carbon monoxide reservoirs are located, whether there are layers of different composition beneath the surface that will be exposed as material sublimates away. For solar system comets observed over multiple orbits, scientists can build detailed models of surface heterogeneity by watching how activity varies with rotation and solar heating. For 3I Atlas, we get one pass, one dataset, and any surface mapping has to be inferred from that limited information. The rotation configuration remains incompletely characterized despite significant effort to understand it. We have estimates of the rotation period, and observations suggest the spin axis orientation may be unusual compared to typical comet populations. But uncertainty margins on these parameters are larger than ideal, because determining rotation state requires either direct imaging, showing surface features rotating in and out of view, difficult with an object this small at these distances, or careful analysis of brightness variations and outgassing jet directions over time. The latter approach is indirect and model-dependent, meaning different assumptions can lead to somewhat different conclusions about rotation parameters. Why does rotation matter so much? Because it determines everything about how sunlight interacts with the surface over time, which in turn controls outgassing patterns, which determine the non-gravitational forces which affect the trajectory. If the rotation is such that certain active regions spend more time in sunlight during the perihelion phase, that creates stronger average outgassing than if rotation kept those regions partially shadowed. The exact spin axis orientation influences whether activity increases symmetrically as the comet approaches the Sun, or whether there are asymmetries that lead to directional thrust. Getting rotation right is essential for predictive models. There's also the question of why this particular rotation configuration, if the unusual orientation findings hold up under further analysis. Rotation states aren't random. They're determined by the comet's formation history and any subsequent collisions or tidal interactions that might have altered its spin. An unusual rotation could indicate an unusual formation process, or it could indicate that the comet experienced a significant event during its journey through space that changed its spin axis. Distinguishing between these possibilities requires more context than we currently have for 3I Atlas specifically, but it's the type of question that becomes answerable when we have dozens of interstellar objects with well-measured rotation states to compare. The origin question looms large in any discussion of interstellar objects. Where did 3I Atlas come from? Not just vaguely interstellar space, but which specific stellar environment ejected it, and when. Efforts to backtrack the trajectory face significant challenges. The velocity vector has uncertainties, especially the components perpendicular to our line of sight. Non-gravitational forces add noise to the trajectory that propagates backward, creating wider cones of possible origin directions the farther back in time you calculate. And stellar motions mean that even if you could perfectly determine where 3I Atlas was millions of years ago, identifying which star it was near at that time requires accounting for how all nearby stars have moved in the intervening period. Some studies have attempted to associate 3I Atlas with known stellar populations or star-forming regions based on its probable past trajectory. These studies are valuable even when they don't produce definitive answers because they constrain possibilities. If the trajectory is incompatible with having originated from certain regions of the galaxy, that narrows the field. If it's consistent with having been ejected from a young stellar system a few million years ago, that tells us something about the typical timescales for such objects to wander between stars. But we're unlikely to ever point to a specific star and say with confidence, that's where 3I Atlas formed. The information just isn't precise enough. Another genuine open question is whether 3I Atlas has a solid core, or whether it's more of a loosely bound aggregate of smaller pieces. This matters for understanding how it formed and how it responds to thermal and rotational stresses. Comets can be relatively solid chunks of ice and rock, or they can be rubble piles, aggregates held together mainly by gravity and weak cohesive forces. Rubble pile comets can break apart more easily under stress, which is relevant for understanding events like the tidal disruption of comet Shoemaker-Levy 9 by Jupiter. For 3I Atlas, no breakup has been observed, which puts some constraints on structural strength, but distinguishing between a solid nucleus and a tightly bound rubble pile requires data we don't have. The broader population question is perhaps the most tantalizing. What's typical versus unusual among interstellar comets? With a sample of 3 objects, we can't answer that statistically. Are most interstellar comets carbon monoxideric like 3I Atlas, or is that unusual even among the broader population? Do most have extreme rotation configurations, or is 3I Atlas an outlier? How does size distribution compare to solar system comets? These questions will become answerable as detection rates increase and the sample grows, but for now, each new interstellar object is data-starved context trying to understand what the population looks like. There's also the matter of how representative our detected sample is of the true population. We're most likely to detect larger, more active interstellar objects that brighten significantly when they approach the Sun. Smaller objects or those with lower volatile content might pass through the inner solar system undetected because they never get bright enough for our surveys to spot. This creates observational bias. The population we see isn't necessarily representative of what's actually out there. Accounting for that bias requires modelling detection thresholds and estimating how many objects we're missing, which is statistically challenging with small sample sizes. Looking specifically at what we might learn from the March Jupiter flyby, there are concrete questions observers hope to address. Will 3I Atlas still be outgassing at that point, months past perihelion and much farther from the Sun? If so, how much? And does the activity follow predictions based on carbon monoxide sublimation models? How precisely can we measure the gravitational deflection by Jupiter, and does it match predictions after accounting for any residual non-gravitational forces? Are there any surprises in how the comet's trajectory responds to the Jupiter encounter, or does everything proceed exactly as orbital mechanics predicts? Each of these questions might seem narrow, but they feed into larger frameworks of understanding. Confirming that carbon monoxide outgassing continues at low levels far from the Sun validates models of how that specific volatile behaves, which informs predictions for future carbon monoxiderish comets. precisely measuring the Jupiter deflection tests, whether we've correctly accounted for all forces acting on the comet, which validates trajectory prediction methods that matter for planetary defense. Finding no surprises during the Jupiter encounter would itself be informative. It would confirm that despite 3I Atlas's unusual characteristics, it still obeys all known physical laws in all circumstances we can test. The long-term question is what happens to our understanding as the sample of interstellar objects grows from 3 to 10 to 50 and beyond. At what point do patterns emerge? When can we start making statements like, interstellar comets typically have this composition range, or rotation states appear to follow this distribution? How many objects do we need to detect before we can confidently say whether something like 3I Atlas is genuinely rare or actually quite common among the population? These are questions about the evolution of a field of study, about how science transitions from case studies to population statistics. There's also the question of whether future missions might attempt to visit an interstellar object. For 3I Atlas specifically, the window is likely passed. Designing, building, and launching a spacecraft takes years, and the comet is already outbound. But for future detections, especially if we get earlier warning through improved surveys, the possibility exists to send a probe for close-up observations or even sample return. Some feasibility studies have explored what would be required to rendezvous with an interstellar object, and while it's technically challenging, it's not impossible with sufficient advance warning and commitment of resources. That hypothetical future mission would answer in hours questions that years of Earth-based observation can only partially address. So the real mystery of 3I Atlas is the mystery of incomplete information. We understand the mechanisms, outgassing, rocket effect, sublimation physics. We have good data on composition and trajectory, but we don't have perfect knowledge of surface structure, exact rotation state, precise origin, or internal properties. Each of those gaps represents a question we can ask and potentially answer with more data, better models, or future observations. They're not mysteries in the sense of scientists have no idea, but in the sense of scientists know what they'd like to find out and are working on it. This is how real science proceeds. You answer the big questions first. Is it dangerous? What's causing the trajectory changes? Is it consistent with natural phenomena? And then you dive into progressively finer details. You acknowledge what you know, what you don't know, and what you need to find out. You're comfortable with uncertainty in the details even as you're confident about the broad picture. And you maintain curiosity about those remaining questions, because each answer expands understanding just a little bit more. For 3I Atlas, the broad picture is solid. Interstellar comet, carbon monoxideric, strong outgassing, unusual but natural characteristics. Safe trajectory taking it out of the solar system. The details are where the remaining work lies, and that work will continue as long as the comet remains observable, and as researchers analyze the data already collected. Those details matter for the cumulative project of understanding what's out there between the stars piece by piece, object by object, observation by observation. As we watch 3I Atlas fade into the distance, becoming a fainter and fainter point of light until it finally drops below detection thresholds, it's worth reflecting on what this entire episode means, not just for astronomy, but for our broader perspective on the universe we inhabit. There's something profound about witnessing an interstellar visitor in real time. For billions of years, objects like 3I Atlas have been wandering through the galaxy, passing through stellar systems, carrying information about distant environments, existing in darkness broken only by the faint glow of distant stars. But until recently, they were invisible to us. We lived on this planet looking up at the sky, completely unaware that occasionally something from beyond our solar system would pass through our neighborhood, unseen and unstudied. Now we see them. Now we track them. Now we extract their stories from the light they reflect and the gases they release. 3I Atlas came from somewhere we'll probably never identify with certainty. It formed in conditions shaped by a different star, possibly ejected during the chaotic youth of that system's planet formation, or perhaps condensed from material in interstellar space itself. It has been travelling for an incomprehensible span of time, through regions of space devoid of warmth or light, carrying within its structure a frozen record of those ancient conditions. And then chance, the vast random dance of galactic dynamics, brought it to our sun. For a few months, as it swung through the inner solar system, we had the opportunity to study it. Telescopes around the world trained on this visitor, capturing its light, analysing its composition, tracking its path. Scientists devoted time and computational resources to understanding its behaviour, to modelling the forces acting on it, to extracting every bit of information possible from this brief encounter. And now it's leaving, returning to the darkness, heading out into interstellar space where it will wander for millions or billions more years, perhaps never coming close to another star. Think about what we learned in that short window. We confirmed that interstellar comets can be rich in carbon monoxide, teaching us about cold formation environments. We observed strong outgassing effects that challenge our models to be more sophisticated. We documented unusual characteristics that expand our understanding of what's possible within natural phenomena. We tested our capability to detect, track, and analyze objects from beyond our solar system, finding that we can do it successfully even when those objects behave in unpredictable ways. Every one of those lessons contributes to the foundation of knowledge we'll use to study future visitors. But perhaps the deepest lesson is about perspective. We are living through a transition in human capability. For the entire history of our species until just a few years ago, we could not detect interstellar objects. The technology didn't exist, the survey telescopes weren't built, the analysis algorithms weren't developed. We theorized that such objects must exist. Probability alone suggested that countless comets and asteroids ejected from other stellar systems must be drifting through the galaxy. But theory isn't the same as observation. Now we observe them. We've crossed a threshold from knowing intellectually that interstellar space is populated with small bodies to directly studying individual examples of those bodies. This is the era we're fortunate enough to live in, an era where the gaps in our knowledge are shrinking, where questions that were once purely theoretical become empirical, where objects from literally alien environments become subjects of detailed scientific investigation. It's easy to take that for granted, to scroll past news about a comet and move on to the next piece of information. But pause for a moment and appreciate what's actually happening. Humans built instruments sensitive enough to detect faint light from a small icy body millions of kilometers away. Humans developed mathematical frameworks precise enough to predict its path and explain deviations from that path. Humans coordinated across institutions and nations to study this visitor comprehensively during its brief time in our neighborhood. That's extraordinary, not in a hyperbolic sense, but in the literal sense of being outside the ordinary, outside what was possible for most of human history. And it's not just about 3i Atlas specifically, it's about what comes next, the infrastructure we're building, the expertise we're developing, the knowledge we're accumulating. All of it prepares us for a future where interstellar visitors are routine observations rather than rare events. We're moving toward an astronomy where the space between stars is no longer a blank unknown but a populated environment we can sample and study through the objects that pass our way. What will we learn when we've detected dozens of interstellar comets and asteroids? How will our understanding of planetary systems, comet formation, and galactic ecology evolve as the sample size grows? What surprises await in that larger dataset? We can't know yet, which is precisely why the work matters. Every object like 3i Atlas brings us closer to answering questions we haven't been able to address. Questions about whether our solar system is typical or unusual, about what conditions exist in the vast spaces between stars, about the diversity of planetary system formation outcomes across the galaxy. And perhaps there's a more personal dimension to this. When you look up at the night sky tonight or tomorrow night, knowing that 3i Atlas is out there, fading as it moves farther from the sun, heading back into the darkness, does it change how you see that sky? Does it make the universe feel a little more dynamic, a little less empty? For me, and for many people who follow these discoveries, it absolutely does. The sky becomes populated not just with distant points of light, but with travelers, with wanderers, with objects that connect our local cosmic neighborhood to the broader galaxy. We're witnesses to something rare, not just in the sense that we're observing a rare object, though we are, but in the sense that we're alive at the right time to see humanity develop this capability. The people who lived before us couldn't detect interstellar objects. The people who live far in the future will take such detections for granted. We'll have so much data that any single object won't seem particularly noteworthy. We're in that transition moment, that brief window where each detection is still special, still surprising, still teaching us things we didn't know before. So what does 3i Atlas mean to you? I'm genuinely curious. Does it spark wonder, curiosity, a desire to understand more about what's out there? Drop a comment sharing your thoughts, and if you want to stay informed as this story continues, as the Jupiter flyby approaches in March, as researchers publish new findings from the data collected, as future interstellar objects are detected, subscribe to this channel. We'll be covering these developments, translating the science into accessible explanations, and continuing to explore the frontier of what we're learning about our universe. The story of 3i Atlas isn't quite over yet. There are still months of observations to come, data to analyse, papers to publish, but its time in the spotlight is waning, and soon it will be just another entry in catalogues, another data point in the growing population of known interstellar objects. Before it fades completely, take a moment to appreciate what it represents: a messenger from another stellar system, a carrier of information about distant environments, a reminder that we live in a galaxy vastly more interesting and dynamic than the static picture the night sky superficially suggests. Until next time, keep looking up, keep questioning, keep wondering about what else is out there, waiting to be discovered. The universe has more surprises in store, and we're living in the age when we finally have the tools to uncover them.